Good evening. Now we will present the solutions to assignment 2. Okay, first we start at question 1. In question 1, we need to find an estimator for theta, which is defined as mu minus mu power to e minus 1. Okay. Since xi obey normal distribution and mu4, so by weak loss of a large number, we can get Sn bar converge to mu. So we get theta hat, which is equal to Xn bar power to e minus 1. Okay, and then by the central limit theorem, we obtain we obtain uh, a convergent relation. Then we define gx, which is equal to x power e minus 1. Therefore, g xn bar, which is equal to theta hat, and g mu, which is equal to theta. Okay, and by delta method, we obtain a new convergent relation. Square root of n times theta hat minus theta, which is converge to normal distribution n 0 4 times 2 times mu power to e. Okay, and the 96%, which is equal to 1 minus the 0.04, which is equal to the probability of theta, which located in a interval from theta hat minus the 0.02 times 2 times mu power to e over square root of m to theta hat plus z plus z 0.02 times 2 times mu power to e over square root of m. Okay, and finally we substitute mu by Sm bar the substitute the 0.02 by 2.0537, and we get the 96 confidence interval for theta. Okay, and now we move to part B. We need to find the confidence interval for a new defined theta. Okay, so we know Xi obey a standard a normal distribution and tan sigma square. So we transfer Xi to a standard normal distribution, and then we define yi, which is equal to xi minus 10 over sigma square, and we get yi obey chi squares distribution. Okay, and now we and now we and now we record the mean and the var of chi square the distribution, we can get EYI, which is equal to 1, and YYI, which is equal to 2, um, because K, which is now which is equal to 1. Okay, and then we define Sn square. Therefore, Sn square over sigma square, which is equal to Yn bar. Okay, and now by central limit theorem, we obtain that this this random sample convergent to normal a standard normal distribution N01. We notice that Sn square, which is converged to sigma square. So Sn square is a consistent estimator for sigma square. Okay, and now we suggest that sigma hat, which is equal to log square root of Sn square. And then we define gx, which is equal to log square root of sigma square times x. And we get g Sn square over sigma square, which is equal to theta hat, and g1, which is equal to theta. By delta method, we obtained this convergent relationship. Then we substitute the Sn square time over sigma square by theta hat and g1 by theta. So we can get this convergent relationship. Okay, and like the step of question 1 part A, we can get the 96 confidence interval for theta. Okay, now and we move to question 2. In question 2, we need to find the likelihood function and find the MLE theta. Okay, so by the definition of maximum likelihood estimate, the likelihood function is L mu, which is equal to 4 power to the probability of y, which is equal to 1, and 6 power to the probability of y, which is equal to -1. Okay, and by the property of standard normal distribution, we could transfer the property y, which is equal to -1, which is equal to 1 minus 5 mu. So we obtain the likelihood function and define L mu, which is equal to log L mu. So uh, eh, oh, so we could which is convenient for me for us to to dif differ differentiate to L mu. Okay, and we differentiate to L mu and let it to equal to 0, and we solve this equation, so we get phi mu, which is equal to 2 over 5. Okay, and we need to now we need to now we differentiate to the L mu, and we find one phi mu which is equal to 2 over 5. We find the differentiation of the L mu is less than 0, so we can get the phi mu is the ML is theta, theta hat. Okay, and we move to question B, part B. Okay, from part A, we know that MLE mu for MLE mu hat for mu satisfies phi mu, which is equal to 2 over 5. And we notice that phi is an injection, so mu hat, which is equal to phi inverse 2 over 5. And now we refer the standard normal distribution table. We could get the estimate of mu is minus 253. Okay, and now we move to the final equation. In part A, we need to calculate the mean and the variance of x. Okay, to calculate the variance of x, so we need to calculate the ex and ex square. And now we use the relation of ex and y and yx, so we could calculate the yx. Okay, and then in part B, we need to prove the theta n hat converge in probability to theta. Since ex is less than positive infinity and yx is less than positive infinity, so by weak law of large number, we can get Xn hat converge to 2 over 2 minus converge in probability to 2 over 2 minus theta. And we notice that 2 times 1 minus 1 over x, this function is continuous. By continuous mapping theorem, we have this function converge in probability to theta. Okay, in question 3, we need use theta n hat to construct an approximated 95 confidence interval for theta with these following data. Okay, we notice that yx is less than positive infinity. So by central limit theorem, we obtain this convergent relationship. Okay, and we define gx, which is we defined 2 times 1 minus 1 over x is equal to gx, and we differentiate to gx. Okay, so by delta method, we could get this convergent relationship, and we use theta n hat to replace gxn bar and use theta to replace g2 over 2 minus theta. So we get this random sample obey normal distribution. So like the step we use in question 1, part A and part B, we could calculate the 95% confidence interval for theta. And we substitute theta by theta n hat. Now we have get this this interval to be the 95% confidence interval for theta. Okay, and in the finally part D, we need to comment the interval gas find in part C for theta. Okay, so how to we comment the interval gas? So we noted the number of the date is 10, but a specific interval gas which needed the number or often more than 30. So we suggest that the true value of theta lies between the confidence interval derived in part C with 95% confidence. But n, which is equal to 10, is a small number. Often we need n is larger than maybe 30. So this interval gas may not be good enough. So we need to you do more to get more data to make a more specific interval gas. Okay, and this is my presentation to the solution of assignment 2. Thank you for your listening.